Imagine looking up at the night sky and realizing that among all those twinkling lights, some of them are keeping secrets so profound they've left astronomers completely baffled. White dwarfs, the incredibly dense remnants of stars like our own sun, have long fascinated scientists with their strange behaviors and extreme physics. But recently, something even more mysterious has emerged from these cosmic ghosts: 25 unexplained signals that defy everything we thought we knew. It's as if the universe is whispering a riddle we're only just beginning to hear. Think about that for a moment. We're not talking about random noise or interference. These are distinct, repeating patterns detected from white dwarfs light years away, signals that don't match any known natural phenomenon. Picture scientists huddled around monitors, their excitement turning to confusion as data streams in that simply shouldn't exist according to our current models of physics. It raises spine-tingling questions. Could these be the echoes of exotic stellar processes we haven't even dreamed of yet? Or might they hint at something even more extraordinary, something that challenges the very boundaries between known science and the unknown? This is where our journey begins, a journey into one of the most captivating space mysteries of our time. Over the next minutes, we'll explore each of these 25 enigmatic signals, diving into the science, the theories, and the sheer wonder of what they might represent. You'll come away not just with knowledge, but with a sense of awe at how much is still left to discover in our vast, mysterious cosmos. So settle in, open your mind, and let's venture together into the heart of this cosmic puzzle. Our journey into the unknown begins with a star in the Virgo constellation, a white dwarf that should have been a quiet, fading ember. Instead, it became the source of our first great mystery. Astronomers monitoring this region detected a signal so peculiar it was initially dismissed as instrumental error, but the signal persisted. It wasn't a random burst of energy or a chaotic flare. It was a precise, rhythmic pulsation. Imagine a heartbeat in the void, a steady, repeating beat of energy arriving from the depths of space with a regularity that mirrors the most precise man-made clocks. The pulse itself is what truly baffles scientists. It has a frequency of approximately 1.23 cycles per minute, a slow, deliberate cadence that doesn't correspond to any known stellar vibration or rotational period for a white dwarf. These remnants of stars are known to pulsate, but their rhythms are typically linked to gravity waves rippling through their dense interiors, creating patterns that are far more complex and much faster. This signal, by comparison, is almost simplistic in its unwavering consistency. Each pulse lasts for nearly 30 seconds with a clear beginning and end, followed by a perfect moment of silence before the next one begins. This duration is another piece of the puzzle that just doesn't fit. It's far too long for any conventional stellar process we understand. Researchers initially scrambled for conventional explanations. Perhaps it was some form of interaction with a hidden companion object, like a planet or a brown dwarf, its material being periodically drawn onto the white dwarf's surface and flaring up. Yet no such object could be found. Another theory proposed it was a new, unknown class of stellar quake, a release of pent-up energy within the star's crystallizing core. But the sheer regularity and clean shape of the pulse wave make this seem unlikely. Natural quakes tend to be messier, with more variation in their output. The most tantalizing and perhaps most troubling early hypothesis came from a small group who suggested this could be evidence of a highly advanced technology. The signal's artificial-seeming precision naturally leads one's imagination toward the possibility of a beacon. However, the scientific community largely cautions against this leap, emphasizing the principle known as Occam's razor. The simplest explanation is usually the correct one. The problem is, in this case, a simple natural explanation has proven utterly elusive. This first signal, the pulsating anomaly, serves as a perfect introduction to our entire list. a clear, unmistakable pattern that speaks a language of physics we have not yet learned to decode. If the steady heartbeat from Virgo felt like a deliberate message, the second signal on our list is more like a staccato burst of cosmic laughter, unpredictable, jarring, and utterly perplexing. This enigma originates from a white dwarf nestled within the sprawling constellation of Cassiopeia, a familiar W shape in the northern sky that now hosts one of the sky's most baffling transmitters. Unlike the metronomic pulse of our first signal, this one manifests as a series of incredibly powerful radio bursts. They aren't random, they repeat. But their intervals are chaotic, arriving without a discernible pattern that would allow astronomers to predict the next one. This lack of rhythm is what makes it so technologically maddening and scientifically fascinating. Detecting this signal was a triumph of persistence and modern technology. Radio telescopes are often tasked with surveying vast swaths of the sky, but they typically focus on specific frequencies or sources for limited periods. Catching a signal that fires off at irregular intervals requires either incredible luck or a new approach. In this case, it was a combination of both, aided by sophisticated software designed to sift through petabytes of archival data, searching for anomalies that earlier surveys might have missed. The discovery team had to rule out a myriad of earthly interferences, satellite communications, radar pulses, even occasional electronic noise from the telescope itself. After a painstaking process of elimination, the source was confirmed. It was indisputably from that distant white dwarf, a point of light that should have been radio quiet. The bursts themselves are incredibly energetic, each one packing more power than our entire sun, emits across the entire radio spectrum in the same brief moment. Yet they are also incredibly short-lived, each blast lasting mere milliseconds. Imagine a flashbulb going off in a dark room over and over, but you never know when the next flash will come. It could be in 10 minutes, or it could be in 10 hours. This irregularity defies our current astrophysical models, which rely on predictable cycles. White dwarfs can flare, but their flares are usually tied to magnetic reconnection events or accretion episodes, which have their own rough timetables and predictable energy signatures. This signal has none of that. Theories attempting to explain it are as varied as the burst intervals themselves. One leading idea involves a deeply magnetic white dwarf with a complex field structure that sporadically snaps and reconnects, releasing these immense bursts of energy. However, for this to produce the observed radio energy, the magnetic field would need to be orders of magnitude stronger than any white dwarf field we've ever measured, pushing into the realm of the theoretical. Another compelling hypothesis suggests an asteroid or a small moon in a highly eccentric orbit around the white dwarf. As this object swings perilously close on its irregular path, tidal forces could rip material from its surface. This material, falling onto the white dwarf, would vaporize and create a temporary hot plasma cloud that might generate such a radio burst upon interacting with the star's magnetic field. The irregular timing of the bursts could then be explained by the chaotic and unpredictable nature of this disintegration process. Yet, even this creative model has its flaws, struggling to account for the sheer raw power of each emission. This leaves us with a profound mystery, a dying star sending out powerful, repeating, yet unpredictable signals that current science cannot fully explain. It serves as a humbling reminder that for all our advanced technology and sophisticated theories, the universe still holds cards it hasn't yet chosen to play. Just when you think the universe couldn't get any stranger, along comes a signal that seems to break the fundamental rules of physics as we know them. Our third mystery takes us to the constellation Lyra, home to a seemingly ordinary white dwarf that is doing something utterly extraordinary. It's emitting bursts of ultra-high-energy gamma rays. This isn't just a little unusual, it's a full-blown cosmic paradox. Gamma rays are the most energetic form of light in the universe, typically produced by the most violent and hottest events imaginable: supernova explosions, colliding neutron stars, or matter falling into supermassive black holes. A white dwarf, especially an older, cooler one like this, is the antithesis of such an environment. It's a stellar cinder slowly cooling down over billions of years. For it to produce such radiation is like finding a glacier that occasionally spits out bolts of lightning and jets of molten lava. The energy level of these gamma rays is what truly staggers the imagination. We're talking about photons carrying trillions of times more energy than visible light. To produce particles with that much kick, you need immensely powerful natural accelerators. Around objects like pulsars or black holes, intense magnetic fields can act like cosmic slingshots, whipping particles to near light speed before they collide and release this extreme energy. But a white dwarf's magnetic field, while strong, is generally thought to be orders of magnitude too weak for this task. Its surface is also far too cool to provide the thermal energy needed for such processes. It's the equivalent of trying to power a massive particle collider like the Large Hadron Collider with a single-A battery. The available energy sources simply don't match the monumental output. So how could this be happening? Astronomers are wrestling with several compelling yet deeply theoretical ideas. One leading hypothesis involves a hidden energetic partner. Perhaps this white dwarf is part of a binary system with a neutron star or even a medium-sized black hole that we haven't been able to detect directly. In this scenario, the powerful gravity and magnetic fields of this unseen companion could be ripping a stream of material from the white dwarf. As this stolen gas is funneled onto the companion, it could be accelerated to incredible speeds, creating a shockwave that produces the gamma rays we observe. The white dwarf itself would be an innocent bystander, its material the fuel for a hidden engine. Another, even more exotic, theory delves into the realm of dark matter. Some physicists have speculated that a dense, ancient object like a white dwarf could act as a natural trap for dark matter particles. If these hypothetical particles were to collide and annihilate each other within the star's core, they could release an enormous burst of energy, potentially in the form of gamma rays. While this idea is highly speculative, it highlights the desperate need for new physics to explain such an outrageous observation. This Lyran signal forces us to confront the possibility that our current models of particle acceleration are incomplete, and that there are mechanisms at work in the quiet corners of the galaxy that we have not yet begun to imagine. Deep within the constellation Ursa Major, a white dwarf is broadcasting a signal of such perfect geometric beauty that it has sparked one of the most intense debates in modern astronomy. This is our fourth signal, a sequence of X-ray pulses that arrives with a symmetry so precise it feels almost engineered. Unlike the chaotic bursts from Cassiopeia or the paradoxical gamma rays from Lyra, this signal is defined by its order. The pulses are spaced in a flawless repeating ratio, a 1-to-1-to-1 pattern where the time between each pulse is exactly identical, creating a rhythm as steady and predictable as a ticking clock designed by the universe's most meticulous watchmaker. The discovery of this pattern presented an immediate and critical challenge for the research team. Was this a genuine astrophysical phenomenon or merely a ghost in the machine, an artifact of the telescope's own electronics? Ruling out instrumental error became a forensic exercise in data analysis. The team pulled in data from multiple observatories, each with its own hardware and software, to see if the pattern persisted across different instruments. It did. They checked for known sources of interference, from passing satellites to cosmic rays striking the detectors. None matched the signal's unique fingerprint. The final, convincing piece of evidence came from pointing the telescope slightly away from the source. The symmetric pattern vanished completely, only to reappear the moment they locked back onto the white dwarf. This confirmed beyond a reasonable doubt that the signal was real and it was coming from that specific point in the sky. This level of mathematical precision is what pushes this mystery into the realm of the profoundly strange. In nature, we often find patterns, but they are usually approximations: the spiral of a galaxy, the orbit of a planet, the vibration of a star. They follow the laws of physics, which allow for slight variations, perturbations, and imperfections. This signal exhibits a kind of perfect integer ratio that is exceptionally rare in natural cosmic phenomena. It's the difference between the organic, imperfect shape of a mountain and the flawless, sharp angles of a crystal. This perfection is what naturally, and perhaps inevitably, leads to speculation about artificial origins. The signal structure is precisely what we might expect from a beacon, a deliberate broadcast designed to announce presence or communicate information across the vast interstellar distances. Of course, the scientific community is rightfully cautious about such an extraordinary claim. Researchers are diligently searching for natural explanations that could mimic such artificial-seeming precision. One compelling theory involves a phenomenally rare orbital dance. Imagine a white dwarf locked in a tight binary system with a pulsar, a rapidly spinning neutron star that emits lighthouse-like beams of radiation. If the orbit of these two dense stellar corpses was perfectly circular and viewed face-on from Earth, the regular eclipsing of one object by the other could potentially create a perfectly timed pattern in the X-ray data we receive. Another hypothesis suggests a resonant vibration within the white dwarf itself, where its crystallizing interior is pulsing at a fundamental frequency with very little damping, creating a clean, pure signal unlike the more complex oscillations we typically observe. Yet, each of these natural models struggles to fully explain the signal's immaculate symmetry over extended observation periods. Gravitational interactions would introduce tiny timing variations over time. Internal vibrations would likely show harmonics or subtle shifts in frequency. The signal from Ursa Major remains stubbornly, perfectly clean. It stands as a testament to the fact that sometimes the universe produces phenomena that sit right on the knife's edge between the known and the unknown, challenging us to broaden our understanding of what is possible. It doesn't necessarily mean we've found evidence of other intelligence, but it powerfully illustrates that nature might be capable of a degree of order we have not yet learned to recognize. After the clockwork perfection of the signal from Ursa Major, the fifth mystery on our list presents a phenomenon that is equally unsettling for the very opposite reason: a sudden and absolute silence. In the constellation of Orion, the Hunter, a white dwarf known to astronomers for decades, has simply stopped. This wasn't a gradual dimming or a signal that slowly faded into the background noise of the cosmos. It was an abrupt, total, and permanent cessation of all emission, as if a cosmic switch had been flipped. For over 30 years, this particular star had been a reliable source of study, emitting a steady stream of low-level radio waves that fit neatly within established models of stellar behavior. Then one day, the data streams from multiple telescopes across the globe all reported the same thing: nothing. The line on the graph went flat and has remained flat ever since. The sheer finality of this event is what makes it so scientifically profound. In astronomy, things change, but they rarely end with such decisive and instantaneous clarity. Stars evolve over millions of years, and even violent events like supernova leave behind expanding remnants that we can observe for centuries. For a process to simply halt suggests a system reaching a critical threshold or a fundamental state change. Researchers were immediately faced with a daunting question: what could possibly happen to an entire star to make it go completely and utterly quiet almost overnight? One of the leading theories involves the concept of crystallization. White dwarfs are essentially Earth-sized spheres of ultra-dense matter, primarily carbon and oxygen, left behind after a star sheds its outer layers. As they cool over billions of years, theory predicts that this super-dense soup of ions will eventually freeze, transforming into a crystalline solid structure, much like water turning to ice. The intriguing idea is that this transition might not be a slow and gradual process from the surface inward. Instead, it could happen catastrophically and rapidly throughout the entire interior once a specific temperature and pressure threshold is crossed. This sudden planet-wide freezing could reorganize the star's internal structure and, crucially, its magnetic field. If the magnetic field, which is partially responsible for generating radio emissions, were to be effectively locked into a new, stable configuration by this instantaneous crystallization, it could abruptly cease its external activity, explaining the sudden radio silence we observe. Another compelling explanation points to a dramatic geological event, but on a stellar scale. We know that the crust of a white dwarf is not a smooth, uniform surface. It's thought to be uneven, with regions of crystallized material and others that are still fluid. It's possible that this crust became structurally unstable, leading to a massive, planet-wide starquake that rearranged the entire surface. This titanic upheaval could have released a vast amount of energy in a single moment, perhaps in a form we weren't observing, like gravitational waves, and in doing so, effectively reset the star's magnetic field to a zero state, shutting down the mechanisms that produced its emissions. Think of it like a circuit breaker tripping in a house, cutting off all power at once. Perhaps the most awe-inspiring possibility is that we witnessed the final act of a cosmic demolition. Some scientists have proposed that the white dwarf may have consumed the last remnants of a surrounding debris disk, the final chunks of a planetary system that once orbited its parent star. As this material, perhaps a large asteroid or a small moon, spiraled inward and was torn apart by the star's immense gravity, it could have created a final, brilliant flash of accretion-powered activity. Once that last meal was fully digested and assimilated, the fuel supply would be completely exhausted, and the star would have no more material to interact with, leading to the sudden and permanent quiet we now observe. This theory transforms the event from a mysterious failure into a natural conclusion, the final period at the end of a very long sentence written in the life of a solar system. Each of these theories offers a glimpse into the extreme and poorly understood physics at work within these stellar embers, reminding us that even in death, a star can still have one last surprise. While the abrupt silence from Orion presented a mystery of finality, the sixth signal introduces a puzzle of constant, deliberate change. Traveling from a white dwarf in the constellation Cygnus, this signal doesn't start or stop, it evolves. It begins as a stable, consistent radio emission, much like the one from Orion before its disappearance. But then, over a period of months, a subtle shift begins. The frequency of the signal, its pitch in the vast radio spectrum, starts to drift. It's a slow, continuous glide, like a musical note sliding seamlessly from a low hum to a higher whistle, and it challenges our very understanding of how these stellar remnants operate over human timescales. This phenomenon, known as a frequency drift, is not entirely unknown in astronomy. We observe it in other contexts, but the causes there don't seem to apply here. For instance, the spinning of a pulsar can slow down over time, a process called spin down, which causes its pulses to arrive at progressively longer intervals. But that's a change in timing, not in the fundamental frequency of the emitted radiation itself. What we're seeing from this white dwarf is different. It's as if the star's internal radio transmitter is being systematically retuned. This kind of change suggests a fundamental physical parameter of the star itself is in flux, which is startling because white dwarfs are supposed to be among the most stable objects in the universe, cooling and settling into retirement over billions of years with glacial slowness. Astronomers are investigating two primary explanations for this gradual drift, each pointing to dynamic processes we've rarely, if ever, witnessed in real time. The first theory focuses on a hidden, decaying orbit. Imagine this white dwarf has a companion, not a star, but a dense, planet-sized object or a brown dwarf. As this object orbits, its gravity could influence the white dwarf's magnetic field or even draw a stream of ionized gas from its surface. If this companion's orbit is not stable, if it's slowly spiraling inward due to the emission of gravitational waves, the environment around the white dwarf would be in a constant state of change. The point of interaction where the inflowing material generates radio emissions would be moving, and the magnetic fields controlling the emission process would be strengthening. This changing environment could directly cause the observed frequency of the radio waves to drift higher as the companion draws nearer, and the entire system becomes more energetic. The second compelling hypothesis involves a profound internal transformation, a changing magnetic field. We often think of a star's magnetic field as a static, fixed structure, but for white dwarfs this may not be the case. As a white dwarf cools and its interior begins the process of crystallization, its magnetic field might not simply vanish or lock into place as with the Orion object. Instead, it could be undergoing a slow, global reorganization. The solidifying core could be expelling magnetic flux, pushing it outward and concentrating it in the star's outer layers. This process would gradually increase the overall strength and alter the configuration of the magnetic field over years or decades. Since the generation of radio waves is heavily dependent on the geometry and strength of these magnetic fields, even a slight strengthening or realignment could manifest as a smooth, continuous drift in the frequency of the emissions we detect. Both of these theories paint a picture of a white dwarf as a far more dynamic and evolving object than our textbooks have traditionally described. They are not simply dead stars cooling in isolation. They can be active participants in complex gravitational dances or undergoing profound internal phase changes that we can witness from light years away. The frequency drift from Cygnus is a slow-motion message, a cosmic indicator that even in these ancient stellar embers, change is still very much afoot. Leaving behind the drifting signal from Cygnus, we arrive at our seventh mystery, one that doesn't involve a changing frequency or a sudden silence, but a peculiar twist in the very nature of light itself. In the constellation of Draco, the dragon, a white dwarf is emitting light that is intensely polarized. To understand why this is so strange, we need to think about ordinary light for a moment. Sunlight, or the light from a typical star, is unpolarized. Its electromagnetic waves vibrate in all possible directions perpendicular to its path, like a crowd of people shaking hands randomly in every direction. Polarized light is different. Its waves are organized, vibrating predominantly in a single plane, like a whole crowd performing a synchronized wave in a stadium. This organized light acts as a powerful diagnostic tool for astronomers. When light becomes polarized, it's usually because it has interacted with something very specific, often a strong magnetic field. The field acts like a filter, forcing the light waves to align with its direction. By measuring the degree and angle of this polarization, scientists can effectively map the structure and strength of a star's magnetic field from millions of light years away. It's a well-established technique, and for many magnetic white dwarfs it works perfectly, revealing orderly dipolar fields similar to a simple bar magnet. The white dwarf in Draco, however, is breaking all the rules. The polarization of its light is off the charts, far stronger than any standard magnetic field model can account for. Even more baffling is its behavior. The angle of polarization, the direction in which the light waves are aligned, doesn't remain fixed. It rotates over time, but not in a smooth, predictable way tied to the star's rotation. Instead, it wobbles and jitters as if the magnetic field itself is chaotically thrashing around beneath the star's surface. This presents a profound contradiction. A white dwarf's magnetic field is thought to be frozen into its incredibly dense, degenerate matter. This means the field should be locked in place, rotating rigidly with the star. The field might be incredibly strong and complex, but it shouldn't be dynamically changing its structure on short timescales. What we're seeing from Draco suggests a magnetic field in a state of violent turmoil, a level of internal activity that defies our understanding of these supposedly placid stellar remnants. One radical theory proposes that we are witnessing the real-time aftermath of a stellar merger. Perhaps two white dwarfs spiraled together and coalesced into a single object. This catastrophic union would have injected a tremendous amount of energy and angular momentum, creating a wildly complex and unstable magnetic field that is still, eons later, trying to settle into a stable configuration. The chaotic wobbling in the polarization could be the dying echoes of this ancient collision, a turbulent magnetic field slowly relaxing into a quieter state. Another, even more exotic, idea suggests that the interior of this white dwarf is not the uniform crystallizing sphere we imagine. It could be a heterogeneous mess with layers of different elements like oxygen, carbon, and neon solidifying at different rates and depths. As these layers freeze, they might be convecting or undergoing chemical separation, and this churning activity in the interior could be constantly generating new magnetic fields through dynamo action, which then punch through to the surface, creating the observed chaotic polarization signal. This would mean the star is not dead and cooling, but is electrically and magnetically active in a way we never thought possible for such an object. This polarized beacon from Draco is a reminder that light carries more than just brightness. It carries information about the forces that shaped it, and in this case, that information is telling a story we are still struggling to interpret. This journey through cosmic oddities now brings us to a white dwarf in the constellation Hercules, an object that appears to be giving off far more heat than it should. This is our eighth signal, a mystery not of strange pulses or silent voids, but of simple excess warmth. Astronomers refer to this as an infrared excess, and while that might sound technical, the concept is beautifully simple. Think of a piece of iron pulled from a forge. It glows brightly at first, but as it cools, its color shifts from white to yellow to red, and eventually it no longer glows visibly at all, though it still radiates heat that you can feel on your skin. A white dwarf is like that cooling ember. By measuring its color and temperature, we can estimate its age and predict exactly how much of this residual heat, this infrared energy, it should be emitting. The white dwarf in Hercules breaks that prediction. It's surrounded by a persistent, unexplained halo of infrared warmth, as if it's sitting beside an invisible campfire that we cannot see. The immediate and most logical suspect for this extra heat is a disk of dust and debris encircling the star. We've actually observed this around other white dwarfs. They are the graveyards of planetary systems. When a star like our Sun dies, it doesn't always go quietly. The violent death throes can destabilize the orbits of planets and asteroids, sending them careening inward. These rocky bodies are then torn apart by the white dwarf's immense gravity, grinding themselves into a fine, hot dust that forms a glowing ring. This dust disk, heated by the star, radiates strongly in the infrared, perfectly explaining an excess. For the Hercules white dwarf, astronomers eagerly went looking for this telltale disk, but the data came back confusing. The signature of the infrared emission was all wrong. It was too smooth, too spread out, and lacked the specific spectral fingerprints of silicate dust, the common stuff of asteroids and rocky planets. It was like detecting the warmth of an oven, but finding none of the expected metal or wiring inside. This puzzling result led scientists to consider more exotic possibilities. Perhaps the source isn't a disk of dust, but a single, larger object, a failed star known as a brown dwarf in a close orbit. Brown dwarfs are too massive to be planets, but not massive enough to ignite fusion and become true stars. They are inherently warm objects, glowing faintly in the infrared from their own residual heat. A brown dwarf companion could easily provide the observed excess warmth. The search began for the gravitational tug of such an object, the slight wobble it would impose on the white dwarf as they orbit a common center of mass. Yet, after years of precise monitoring, no such wobble has been detected. The star holds its position with a steady resolve, offering no evidence of a hidden partner massive enough to be the culprit. With the standard explanations falling short, researchers have had to venture into more speculative territory. One fascinating idea is that we are seeing the thermal glow of a tightly swaddled family of exomoons. If a giant planet survived the star's death and migrated inward, its system of moons could have been stripped away and pulverized, not into a neat disk, but into a vast cloud-like swarm of debris. This cloud would envelop the white dwarf, absorbing its light and re-radiating it as a diffuse, uniform infrared glow that lacks the sharp features of a traditional dust ring. Another, even more intriguing hypothesis involves a captured rogue planet. These are planetary mass objects that are ejected from their star systems and wander the galaxy alone. It's possible that such a nomadic, ice-rich world ventured too close to the white dwarf and was captured into a distant, highly elliptical orbit. As it makes its closest approach, the intense tidal forces from the star's gravity flex and heat its interior, causing it to vent geysers of water vapor and other volatiles into space, creating a temporary, warm atmosphere around itself that contributes to the infrared excess we detect. Each of these theories is compelling, yet each also has its own flaws and unanswered questions. The infrared excess from Hercules remains a persistent, warm enigma. It challenges our assumptions about the final stages of planetary systems and suggests that the environments around these dying stars may be far more diverse and dynamically complex than we ever imagined, filled with unseen objects and processes that leave only a faint thermal signature as their calling card. Nestled within the great winged horse of the Pegasus constellation, a white dwarf delivered a mystery so brief it was almost missed entirely. A single, brilliant flash of X-rays that blazed into existence and vanished all within the span of a few milliseconds. Capturing this ninth signal was a feat of modern astronomical luck and automated vigilance. It wasn't found by an astronomer patiently at an eyepiece. It was detected by a sophisticated algorithm tirelessly sifting through the raw data stream of an orbiting X-ray observatory. The software is designed to recognize statistical outliers, and this was a supreme outlier. A spike of energy so intense and so fleeting that it stood out like a lightning strike against the placid background of the cosmos. By the time the alert was generated and human eyes saw the data, the event was already hours in the past, a ghost in the digital machine pointing to a location where nothing unusual seemed to remain. The sheer brevity of this event is its most defining and puzzling characteristic. In the realm of astrophysics, duration often provides crucial clues about the physical scale of an event. A long, drawn-out gamma ray burst points to the collapse of a massive star, while the rapid flickering of a pulsar speaks to its small, dense nature. An event that lasts mere milliseconds implies an origin point that cannot be more than a few hundred kilometers across. The light travel time across the source must be shorter than the event itself. This neatly matches the size of a white dwarf, but it creates a colossal energy problem. To release such a tremendous amount of high-energy X-rays in such an impossibly short window requires an almost unimaginable power density, a focused eruption that, for its brief duration, outshines entire galaxies in the X-ray spectrum. Explaining this transient flash pushes the limits of known physics. One compelling theory involves a special kind of nova event, but on an incredibly compressed timescale. White dwarfs in binary systems can pull hydrogen-rich material from a companion star. This gas accumulates on the white dwarf's surface until the pressure and temperature at the base of this layer become so extreme that it triggers a runaway thermonuclear explosion, a classical nova. These events are bright, but they typically build to a peak over days and fade over weeks. For the Pegasus event, theorists propose a micronova or a hyper-fast nova, where the ignition happens not across a large portion of the surface, but is instead channeled and concentrated by the star's magnetic field onto a very small area, perhaps near one of its magnetic poles. This would focus the entire explosive force into a tight beam, resulting in an incredibly brief, incredibly intense flash of radiation directed like a cosmic blowtorch. If this beam happened to be pointed directly at Earth, we would see exactly what was observed, a millisecond flash of unimaginable power. Another, more exotic possibility is the sudden and catastrophic destruction of an asteroid made of extremely dense material. If a solid iron-nickel asteroid the size of a small city were on a collision course with the White Dwarf, its final moments would be spectacular. As it plunged through the star's intense gravitational field, tidal forces would compress it violently. Just milliseconds before impact, the immense pressure could trigger a form of explosive nuclear fusion on the asteroid's surface, as its own material is used as fuel for a final, devastating flash. This would be less of an impact and more of a bomb going off at the doorstep of the star. The resulting fireball of plasma, heated to billions of degrees, would emit the intense burst of X-rays before the entire event was swallowed by the White Dwarf without a trace. The challenge with both of these theories and all others is the lack of a repeat performance or any aftermath. A classical nova leaves behind an expanding shell of ejected material that can be studied for years. The collision of a dense asteroid might leave a temporary hotspot on the star's surface, yet follow-up observations of this region in Pegasus have revealed nothing. No expanding debris, no changes in the star's brightness, no residual heat. It is as if the event never happened, leaving behind only a single perfect data point that defies easy categorization. This transient flash embodies the ultimate challenge in astronomy. How do you solve a puzzle when the only piece you have is the memory of its disappearance? If the millisecond flash from Pegasus was a cosmic shout, the 10th signal is more like a complex chord played across the cosmos, traveling to us from a white dwarf on the outskirts of the great Andromeda galaxy. This phenomenon isn't a single tone but a cascade of them, a set of harmonically related frequencies that ring out together in a display of celestial synchronicity. Think of it like striking a tuning fork. You hear the primary note, the fundamental frequency, but also ringing above it are the fainter, higher-pitched overtones, the harmonics. These are integer multiples of the base frequency. If the fundamental is 100 Hz, the harmonics would be 200, 300, 400 Hz, and so on. That is precisely the pattern astronomers detected, a fundamental radio pulse with a series of perfect harmonic echoes ringing out at double, triple, and even quadruple the base frequency. In the engineered world of human technology, harmonic frequencies are commonplace. They are the hallmark of designed systems, from musical instruments to radio transmitters, where vibrations are carefully controlled to create these pleasing mathematical relationships. Finding such a precise harmonic series emanating from a natural object in deep space immediately raises an eyebrow. It suggests a resonant cavity, a system where energy is bouncing back and forth in a confined space, amplifying certain frequencies and cancelling out others, much like the column of air inside a flute shapes the sound it produces. The core scientific challenge is to identify what, in the brutal environment around a white dwarf, could possibly act with such acoustic precision. The most promising natural explanation points to the star's magnetosphere, the vast region of space dominated by its magnetic field. Within this invisible structure, clouds of electrified gas or plasma can become trapped. Theorists propose that a specific type of plasma wave, called an electron-cyclotron maser instability, could be at work. In this process, electrons spiral along the powerful magnetic field lines and, under the right conditions, can amplify radio waves at a specific frequency tied directly to the strength of the magnetic field. The harmonic frequencies could then arise if this maser action occurs not just at the primary location, but simultaneously at other points along the field line where the magnetic strength is exactly half, a third, or a quarter of the original value, naturally generating the observed harmonic series. It would be a case of the star's own magnetic architecture acting as a complex natural amplifier. However, this elegant model faces significant hurdles. For the harmonics to be as clean and distinct as those observed, the plasma environment would need to be incredibly stable and uniform, which is difficult to reconcile with the turbulent, chaotic conditions we typically associate with these stellar remnants. Even a small amount of turbulence would smear the precise frequencies, blurring the harmonic lines into a noisy mess. Furthermore, to produce the sheer power of the observed signal, the efficiency of this natural maser would have to be pushed to its absolute theoretical limits, operating in a regime we have never confidently observed in nature. This forces a re-examination of even more exotic possibilities, such as the resonant vibrations of the white dwarf's solid core itself. As the core crystallizes, it could form a sphere capable of ringing like a giant bell when struck by a starquake or an impact. The fundamental tone would be the entire sphere pulsating, while the harmonics would represent more complex patterns of vibration across its surface. While this could produce the right frequencies, transferring that immense vibrational energy from the solid core through the dense liquid mantle and into the plasma of the magnetosphere to be broadcast as radio waves is a physics problem of daunting complexity. The harmonic signal from Andromeda stands as a beautiful and frustrating puzzle, a natural symphony whose conductor and orchestra remain hidden from view. While the harmonic symphony from Andromeda played with the purity of mathematical ratios, our 11th signal presents a spectacle of frantic, high-speed motion. In the constellation Perseus, a white dwarf is exhibiting a behavior that makes astronomers double-check their instruments. Its spectral lines are shifting back and forth at a dizzying pace. To understand why this is so disconcerting, we need to revisit a fundamental tool of astronomy, the spectrum. When starlight passes through a prism or a spectrograph, it splits into a rainbow. But this rainbow is not perfect. It's crossed by dark lines like a unique barcode. Each line corresponds to a specific chemical element in the star's outer atmosphere, absorbing light at a precise wavelength. The position of these lines is the star's fingerprint, and it's supposed to be stable. The magic of these lines is that they can move. The Doppler effect, the same phenomenon that makes a siren's pitch change as it races past you, applies to light. If a star is moving toward us, its light waves get compressed, shifting the entire spectral fingerprint slightly toward the blue end of the spectrum. If it's moving away, the waves stretch, creating a red shift. By measuring the precise amount of this shift, astronomers can calculate the star's velocity along our line of sight with breathtaking accuracy. The white dwarf in Perseus, however, isn't exhibiting a steady, predictable velocity. Its spectral lines are performing a frantic dance, wobbling and shifting over periods of just hours, indicating that the star's atmosphere is seemingly surging toward and away from us at velocities reaching thousands of kilometers per second. This kind of rapid, large-scale motion is unprecedented for such an object. A white dwarf is a gravitationally locked sphere of ultra-dense matter. Its entire structure is defined by stability. It can't be physically wobbling back and forth that quickly. The forces required to accelerate an entire star to such speeds and then decelerate it again in a matter of hours would be cataclysmic and would tear the star apart. Therefore, the shifting lines must be telling a different, more complex story about activity in the star's atmosphere or its immediate environment, rather than the motion of the entire body. One compelling theory suggests we are witnessing a violent gravitational treadmill. Imagine a massive, Jupiter-sized planet that survived the star's death throes, now locked in a dangerously close eccentric orbit. As it swings around the white dwarf, its immense gravity would exert a powerful tidal pull on the star's outer layers. This wouldn't move the whole star, but it could literally drag the photosphere, the star's visible surface, distorting it into a football shape. One hemisphere of the star would be pulled toward us while the opposite side is stretched away. As the planet orbits, this distorted region would rotate with it, creating the illusion of a rapidly changing velocity as we observe different parts of the bulging atmosphere moving toward and away from us. This could perfectly explain the rhythmic, high-speed spectral shifts. Another hypothesis points to colossal stellar storms, but on a scale we can scarcely imagine. On our Sun, solar flares and coronal mass ejections can propel material outward at high speeds. On this white dwarf, a continuous series of such eruptions, perhaps fueled by a tremendously powerful and unstable magnetic field, could be launching vast plumes of plasma from its surface. We would see one event. A plume erupts on the side of the star rotating toward us. Its material Doppler shifted toward the blue as it rockets in our direction. Hours later, as the star rotates, we might observe the aftermath of an eruption on the receding side, with material shifted to the red as it flows away. The rapid changes in the spectral lines would then reflect the chaotic and violent weather in the star's atmosphere, a tempest of epic proportions. Yet, each of these otherwise elegant explanations faces a significant challenge: energy. The velocities implied by the spectral shifts are simply too high, accelerating entire sections of a stellar atmosphere to thousands of kilometers per second, whether through tidal distortion or magnetic eruption, requires an energy source far beyond what standard models allow for a cooling stellar remnant. It would demand a reservoir of energy that we cannot currently account for, suggesting our understanding of the inner workings or the environmental interactions of these white dwarfs is still profoundly incomplete. The dancing spectral lines of Perseus are a vivid reminder that a star's light is a messenger, and sometimes the message it carries is one of chaos and power that we are only beginning to translate. Leaving behind the atmospheric turmoil of Perseus, our journey brings us to a white dwarf in the constellation Leo that is engaged in a far more subtle, yet no less mysterious performance. It is rhythmically winking at us. This 12th signal is not about a strange emission or a violent shift, but an absence. At impeccably regular intervals, the star's light dims by a precise, small percentage before returning to its normal brightness. This periodic dimming is the classic signature of an object passing in front of the star from our vantage point on Earth, a phenomenon we've used to discover thousands of exoplanets. But in this case, the familiar explanation falls apart, leaving astronomers staring at a light curve that simply doesn't make sense. When a planet transits its star, the pattern is usually clean and predictable. The light dips as the planet's disk begins to obscure the star, holds at a steady minimum while the planet is fully in front, and then rises again as it moves away. The depth of the dip tells us the size of the planet relative to the star. Here's the first anomaly. The dimming of the Leo white dwarf is far too shallow to be caused by a Jupiter-sized planet, yet far too deep and complex to be caused by an Earth-sized one. The light doesn't bottom out into a flat plateau, it dances. The dimming is structured with subtle variations in the middle of the event that suggest we are not looking at a single, solid object, but at something with intricate structure, something that is partially transparent or highly irregular. This immediately launched a hunt for a conventional culprit. Could it be a tightly packed swarm of asteroids or comets, a cloud of debris on a precise orbit? While a debris cloud could explain the complex shape of the dimming, it presents a massive stability problem. Such a cloud, subject to the intense gravitational and radiation forces so close to a white dwarf, should dissipate or be pulled apart on a very short timescale. It could not maintain the clockwork regularity observed over many cycles. The orbit itself is another puzzle. It's very close to the star with a period measured in hours. For a planet to survive the star's violent red giant phase and end up in such a tight orbit is statistically improbable, and no gravitational tugs from a hypothetical companion star have been found to explain how it might have migrated inward after the fact. The failure of these standard models is what opens the door to more speculative and frankly thrilling possibilities. One of the most debated ideas is the concept of a disintegrating planet. Imagine a rocky world that ventured too close to the white dwarf's searing radiation. The fierce light could be literally boiling the planet's surface away, creating a vast, trailing tail of vaporized rock and dust, much like a comet. This tail would be irregular and constantly shifting, which could account for the complex dimming structure. The planet itself, slowly being devoured, would be the anchor point ensuring the event repeats with orbital precision, while its disintegrating body creates a different silhouette during each transit. Then, of course, there is the hypothesis that inevitably captures the public imagination. The megastructure concept, popularized as a Dyson sphere, or in this case, more likely, a vast orbiting array designed to harness the star's energy. From a purely observational standpoint, a partially completed swarm of giant solar collectors would produce an irregular, structured dimming pattern that could perfectly match the data. It is a seductive idea, a potential signature of intelligence on a scale we can barely comprehend. However, astronomers are quick to apply intense skepticism to this notion. The universe is under no obligation to be mundane, but it has consistently shown that natural explanations, once discovered, are often more astonishing than any fiction. The burden of proof for such an extraordinary claim is rightly astronomically high. This ongoing debate between the exotic natural and the artificial is the heart of the mystery in Leo. It isn't just about solving one puzzle, it's about a fundamental challenge to our methods of interpretation. We are forced to ask when we see something that walks like a duck and quacks like a duck, but we're looking at it through a telescope from light years away. How certain can we ever be that it isn't some other unknown animal entirely? This periodic dimmer doesn't just challenge our models of planetary systems. It challenges the very process of how we deduce cause from effect across the unimaginable gulf of interstellar space. Moving from the complex transit puzzle in Leo, we encounter a white dwarf in the constellation Boots that is broadcasting a signal that sounds mundane to astronomers but is, in reality, a profound violation of stellar retirement rules. This 13th signal is the clear, steady emission of non-thermal radio waves. To grasp why this is so baffling, we need to understand the fundamental difference between thermal and non-thermal radiation. Think of a stove burner. When it's off, it's cold and dark. As you turn it on, it heats up, first glowing a dull red, then orange, and if it could get hot enough, it would eventually emit blue light and even invisible ultraviolet radiation. This is thermal radiation. Its properties are dictated solely by the object's temperature. The color and intensity tell you how hot it is. Most of the light we get from stars, including the white-hot glow from a young white dwarf, is thermal. Non-thermal radiation is a completely different beast. It doesn't come from simple heat. Instead, it's generated by subatomic particles, like electrons, being whipped around at nearly the speed of light by powerful magnetic fields or shock waves. As these frenetic particles are accelerated, they release energy, often in the form of radio waves, but this emission is not tied to the temperature of the source material. The most famous examples of non-thermal emitters are pulsars spinning neutron stars with colossal magnetic fields that act like cosmic power plants, accelerating particles and beaming radiation across the galaxy. A quiet, elderly white dwarf, however, is the astrophysical equivalent of a retired person enjoying a calm life. It's not supposed to be running a particle accelerator in its backyard. The white dwarf in Boots is precisely that, an elderly, cool star. By measuring its temperature and color, astronomers have confidently placed it among the older population of these stellar remnants, a quiet ember that has been cooling for billions of years. Its magnetic field, while present, is measured to be relatively modest, nothing like the powerhouse fields of a pulsar that could easily generate such non-thermal emission. This creates a glaring contradiction. The star possesses all the hallmarks of a peaceful, quiet retirement, yet it is producing a vigorous, energetic signal that implies a hive of violent particle activity. It's as if we detected the powerful radio broadcast of a massive antenna array, but upon arriving at the source, we found only a silent, dark rock. So where is this energy coming from? How is this cool, dense sphere managing to accelerate particles to such fantastic speeds? One compelling theory revisits the idea of a hidden companion, but not a star. Perhaps a Jupiter-sized planet or a brown dwarf is locked in a close orbit with the white dwarf. The star's gravity could be brutally stripping material from this companion, pulling it into a swirling accretion disk. As this gas spirals inward at tremendous velocity, it could generate intense magnetic turbulence and shocking collisions, the perfect environment for accelerating electrons and producing the observed non-thermal radio waves. The white dwarf itself would be the gravitational anchor for this violent process, but the actual particle acceleration would be happening in the chaotic disk of material surrounding it. Another, more self-contained hypothesis suggests that the star's own magnetic field is far more complex and dynamic than our simple measurements can detect. What if the field isn't a stable, simple dipolar shape but a tangled multipolar mess? Regions where these magnetic field lines knot and cross could act as natural reconnection sites, suddenly releasing stored magnetic energy in explosive bursts. These events could propel local pockets of electrons to relativistic speeds, generating the non-thermal radio emission. This would mean the white dwarf isn't entirely dead. It still possesses a kind of magnetic weather, with occasional storms powerful enough to light up our radio telescopes across the light years. The existence of this signal in Boots forces a significant reassessment of what we thought we knew about stellar evolution's final chapter. It suggests that even the oldest and calmest-looking white dwarfs may be capable of harboring unseen ferocity, either through destructive interactions with their planetary systems or through violent internal magnetic processes that leave no visible trace on their placid surfaces. This non-thermal broadcast is a powerful reminder that a star's age does not necessarily dictate its activity, and that the tools we use to classify these objects may be missing a crucial, energetic piece of the puzzle. While the non-thermal radio signal from Boots presents a puzzle of unexpected energy, the 14th signal on our list introduces a mystery of breathtaking cosmic coordination. From a white dwarf in the constellation Gemini, astronomers have detected something that initially seemed like a happy coincidence, but has since revealed itself to be a profound enigma: perfectly correlated emissions across multiple wavelengths. This means that whenever this star flares up in radio waves, it flares up in X-rays and in optical light at the exact same moment, with the same intensity profile. It's as if the universe is playing a single chord across the entire electromagnetic spectrum, with each note rising and falling in perfect lockstep harmony. Such perfect correlation is exceptionally rare in astrophysics. Most cosmic objects are messy and complex, with different types of emission often generated by separate physical processes that operate on different timescales. A star might have a flare in visible light caused by surface activity, while its radio waves are generated by processes in its magnetosphere. These events might be related, but they rarely happen with such precise, simultaneous timing. The flawless lockstep observed in Gemini suggests a single, unified engine, a primary event that instantaneously drives the entire orchestra of emissions. This level of coordination points to an incredibly efficient and direct energy transfer mechanism, something that our current models of white dwarf physics struggle to account for. The hunt for a unifying theory has led researchers down several fascinating paths. One prominent idea centers on a phenomenon known as a magnetic catapult. Imagine the white dwarf's powerful magnetic field as a vast, twisted web of rubber bands storing immense energy. When this field undergoes a sudden reconfiguration, a snap called magnetic reconnection, it acts like a slingshot, explosively accelerating electrons to nearly the speed of light. These ultra-relativistic electrons then become the universal key. As they spiral along the star's magnetic field lines, they naturally generate radio waves through a process called synchrotron radiation. Simultaneously, when these same high-speed electrons collide with photons of visible light starlight, they boost them to much higher energies, creating X-rays in a process known as inverse Compton scattering. In this elegant model, a single event, the magnetic snap, creates the initial pool of energetic particles that then immediately and efficiently produce the correlated emissions across all observed wavelengths. An alternative, equally compelling theory involves an accretion-driven shock. This scenario proposes that the white dwarf is steadily feeding on material from a faint, low-mass companion star or a surrounding debris disk. As this stream of gas plummets toward the star's surface, it doesn't land softly. Instead, it slams into the star's magnetosphere at a significant fraction of the speed of light, creating a standing shock wave, a perpetual cosmic traffic jam of superheated plasma. This shock would be a fantastic multi-wavelength engine. The violent collisions within the shock would heat the material to millions of degrees, causing it to glow intensely in X-rays. The turbulent, magnetized environment of the shock itself would also be a perfect site for accelerating electrons and generating strong radio emissions. And the optical light could simply be the thermal glow of the hot, shocked gas itself. A small change in the accretion rate would affect the entire shock at once, causing all three emissions to rise and fall together in a perfectly synchronized dance. The profound implication of both theories is that we may be looking at a white dwarf operating in a hybrid state, blurring the lines between different classes of stellar objects. It could be exhibiting the magnetic fury of a pulsar but on a smaller scale, or the accretion-powered intensity of a black hole binary system but with a solid surface. This Gemini object challenges the neat little boxes into which we like to sort celestial phenomena, forcing us to consider that a white dwarf's lifestyle can be far more active and interconnected than we ever believed. Its correlated signal is a masterclass in cosmic efficiency, demonstrating how a single, violent event can echo across the entire spectrum of light, leaving us with a synchronized mystery that is as beautiful as it is baffling. Now we pivot from the harmonious multi-wavelength chord in Gemini to a signal that feels more like a cosmic argument, a direct contradiction playing out in the light from a white dwarf in the constellation Libra. This 15th signal presents scientists with a confounding anti-correlation, a precise and consistent inverse relationship that defies intuitive logic. When this star grows brighter in visible light, it grows dimmer in X-rays. When it fades optically, its high-energy X-ray emission surges. It's as if the star has two separate volume knobs controlling its energy output, and they are permanently wired to work against each other, one turning up as the other turns down. This seesaw behavior is a direct challenge to our basic understanding of energy transfer and storage in these stellar remnants. In most physical systems we observe, different forms of emission tend to be positively correlated. A more energetic event typically makes an object brighter across multiple wavelengths simultaneously, as we saw with the previous signal. An anti-correlation is far more unusual and intellectually tantalizing because it suggests a competitive process, a fundamental trade-off where energy channeled into one output must be stolen from another. For the astronomers studying it, this isn't just a quirky observation. It's a vital clue about the inner workings of this white dwarf, a clue that current models are struggling to interpret. One compelling explanation frames this as a tale of two reservoirs. Imagine the white dwarf's atmosphere contains two competing pools of energy. The first pool fuels the optical brightness, the thermal glow of the star's hot surface. The second pool is responsible for generating the X-rays, likely through the acceleration of particles in its magnetic field. The anti-correlation suggests that these two reservoirs are connected, but that energy can be transferred from one to the other. A leading theory proposes that the star's magnetic field acts as the intermediary in this cosmic energy swap. During periods of relative magnetic calm, energy can build up at the surface, causing the star to glow more brightly in visible light. But when the magnetic field becomes unstable and undergoes a reconnection event, it siphons that built-up thermal energy away from the surface, using it instead to accelerate electrons to near light speed. These high-speed particles then produce X-rays when they interact with the magnetic field, all while the surface, now deprived of its extra energy, temporarily dims. An alternative hypothesis shifts the focus from the star's interior to its immediate environment. This model suggests the white dwarf is surrounded by a thick, opaque shroud of gas, a corona of sorts, but far more substantial than our Sun. This shroud would be excellent at absorbing the high-energy X-rays produced deep within the magnetosphere, preventing them from escaping into space. However, the same shroud, when heated by this absorbed X-ray energy, would itself glow brightly in optical and ultraviolet light. In this scenario, we are not seeing the star's true surface at all, but the outer layer of this obscuring cloud. When the internal X-ray engine is running strong, it heats the shroud, making it glow brightly in optical light while simultaneously blocking our view of the X-ray source. When the internal engine sputters and X-ray production drops, the shroud cools and becomes more transparent, allowing the weaker X-rays to finally escape while its own optical glow fades. It's a complex game of hide and seek where the hiding place itself is the source of the light we see. This anti-correlation is more than just a puzzle, it's a powerful diagnostic tool. By meticulously measuring the exact timing and magnitude of these opposing brightness changes, astronomers can effectively peer into the engine room of this white dwarf, testing which of these theoretical models, the magnetic energy siphon or the obscuring shroud, best fits the data. The signal from Libra forces a move away from simple, one-dimensional thinking and demands a more integrated view of these stars as complex systems where atmosphere, magnetic field, and immediate environment are in a constant, dynamic, and often counterintuitive conversation. This 16th signal takes us to the heart of the Crab constellation, where a white dwarf is flickering with an almost unbelievable rapidity. The oscillations detected here aren't merely fast, they are among the most rapid coherent variations ever recorded from such an object, with the entire rise and fall of each pulse occurring in mere seconds. To put that into perspective, consider that a typical white dwarf pulsation, driven by gravity waves, might have a period of several minutes. This is something else entirely, a frantic, high-frequency shuddering imprinted on the star's light, as if its entire surface is vibrating like a struck drumhead at a pitch we can barely register. The sheer speed of these oscillations is the first major clue and the first major problem. In physics, the timescale of an event is often a direct proxy for its physical size. Very fast events must originate from small regions. The rapid flickering suggests the source of this activity is confined to a relatively tiny area on or above the star's surface, perhaps no larger than a single continent on Earth. Yet, the amount of energy being released in each of these rapid flashes is immense, requiring a power source that is both incredibly concentrated and highly efficient. This immediately rules out large-scale surface activity or global processes, pointing instead to a localized but extremely violent event happening over and over again. Two primary natural explanations have emerged from the scientific debate, each compelling yet fraught with its own challenges. The first theory points to a series of continuous micro-scale starquakes. The crust of a white dwarf under unimaginable pressure is thought to be brittle. As the star cools and its interior crystallizes, this solid crust must adjust, potentially fracturing under the strain. A major quake would be a rare cataclysmic event, but what if we're seeing the opposite? What if the crust is experiencing a constant torrent of tiny, localized tremors? Each microquake would release a small burst of energy as the crust snaps and shifts, producing a brief, sharp flash of light. The rapid succession of these flashes could create the observed oscillating light curve. The challenge for this model is the incredible regularity and persistence of the signal. Tectonic activity, even on a stellar scale, tends to be more random and clustered rather than forming such a steady, rapid rhythm. The second, and perhaps more favored, theory involves a relentless barrage of magnetic reconnection events. Imagine the White Dwarfs' magnetic field as a tangled web of energy. At points where opposing field lines are forced together, they can suddenly snap and reorganize into a lower energy configuration, a process called magnetic reconnection. This event releases a tremendous amount of stored magnetic energy in an explosive burst, accelerating particles and heating plasma to extreme temperatures which would flash brightly. This phenomenon is well documented on our own sun, creating solar flares. On this white dwarf, the scale would be vastly larger. The rapid oscillations could be explained if the magnetic field is in a state of constant, stressed turmoil, with tiny reconnection events going off like a string of firecrackers in one active region. The magnetic field would act as a trigger, ensuring each event is similar in size and duration, creating the coherent, rapid pulses we detect. However, both of these models hit a significant snag: confirmation. For the starquake hypothesis, we would expect to see specific changes in the oscillation frequencies over very long timescales as the star's structure gradually evolves, but such changes have not been observed. For the magnetic reconnection model, we would expect the oscillations to be strongly polarized, as the process is inherently tied to the magnetic field's geometry. While some polarization has been detected, it isn't as clear-cut and definitive as the models predict. This lack of a smoking gun leaves both theories in a state of plausible uncertainty. The rapid oscillations from Cancer remain a breathtaking phenomenon, a glimpse into the energetic turmoil that can rage on even the most seemingly placid of stellar remnants, reminding us that stability is often just an illusion from a distance. Among the frantic flickering and contradictory emissions we've explored, the 17th signal offers a different kind of mystery, one of profound and silent absence. In the constellation Ophiuchus, the serpent-bearer, the light from a white dwarf passes through our telescopes and into a spectrograph where it is stretched out into its constituent colors. And there, in this cosmic rainbow, astronomers found lines that shouldn't be there, dark gaps in the spectrum where light has been absorbed. These are not just any absorption lines, they are complete strangers, a set of spectral fingerprints that do not match the identity of any known element in the universe. This discovery sent chemists and physicists scrambling back to their databases and their fundamental principles. The process of identification is methodical and precise. Every element, when heated or when existing in the atmosphere of a star, absorbs light at specific, unique wavelengths determined by the quantum energy jumps of its electrons. It is a universal barcode system, and we have a complete catalog for every element on the periodic table, from hydrogen to oganesson. The team in Ophiuchus ran the unknown lines through this entire catalog, and one by one, every possible match was rejected. The wavelengths were close to some known elements, but never exact, and the patterns of multiple lines together didn't correspond to any element's known spectral signature. It was as if they had found a set of footprints that had 6 toes, similar to a human print but fundamentally, undeniably different. The immediate and most thrilling possibility is that we are seeing the signature of an unknown form of matter. One leading hypothesis points toward exotic aggregations of particles that are theorized but have never been observed in nature. For instance, quark matter, a soupy state of subatomic particles that may exist under conditions of immense pressure, could potentially produce entirely new spectral lines if it were present on or near the surface of the white dwarf. Another idea involves strange matter, a hypothetical substance containing strange quarks that is thought to be more stable than ordinary matter under extreme densities. If chunks of this strange matter were to exist and be vaporized in the star's atmosphere, they could imprint these bizarre, unidentifiable lines onto its light. Yet, an even more radical explanation is gaining traction, that the lines are not from new matter, but from old matter behaving in a new way. The intense gravitational field on the surface of a white dwarf is hundreds of thousands of times stronger than Earth. This incredible gravity can profoundly affect the very atoms themselves, warping the electron orbitals in ways that subtly change the wavelengths of light they absorb. While physicists can calculate these shifts, known as gravitational redshifting, the observed lines in Ophiuchus don't align perfectly with these predictions either. This discrepancy has led a few scientists to speculate that we might be glimpsing evidence of physics beyond our current models. Perhaps the rules of quantum mechanics, which govern these electron energy levels, are ever so slightly different under such extreme conditions, suggesting a chink in the armor of our most fundamental theories. The true enigma of the Ophiuchus lines is their stubborn refusal to be categorized. They are not a transient flash or a rhythmic pulse. They are a permanent, stable feature in the star's spectrum, a constant and quiet statement of an anomaly that is simply there. This persistence argues against a one-time event like an impact and for an ongoing process or a permanent constituent of the star's atmosphere. It forces us to confront the humbling reality that despite our detailed maps of the atomic universe, there are still territories that remain blank, waiting for a new generation of explorers to finally chart their meaning. Emerging from the depths of Aquarius, the 18th signal introduces a mind-bending characteristic not of what is being emitted, but how it is being delivered. This white dwarf is producing a beam of radiation so intensely focused and directional that it sweeps across the galaxy like a cosmic lighthouse, and for a brief, dazzling moment every 19 hours, that beam flashes directly across our solar system. This phenomenon of beaming is a hallmark of pulsars, rapidly spinning neutron stars whose powerful magnetic fields funnel radiation into tight cones emanating from their magnetic poles. When one of those poles is aligned with Earth, we see a pulse. For a white dwarf, a star with a much weaker magnetic field and a rotational period typically measured in hours or days, such a clean, powerful beam is deeply anomalous. It's the difference between a bare light bulb glowing in all directions and a laser pointer projecting a coherent ray across a dark room. The challenge for astronomers is reconciling this pulsar-like behavior with a white dwarf's inherent physical limitations. A neutron star's incredible density and magnetic field strength are what allow it to act as a natural particle accelerator and create such tightly collimated beams. A white dwarf simply doesn't have the raw power for this under normal circumstances. So how is this one managing it? The leading theory involves a phenomenon called precession. Imagine a spinning top just as it starts to slow down. Its axis of rotation begins to slowly wobble in a circle. This wobble is precession. Now imagine this white dwarf is not a perfect sphere. Its powerful magnetic field, which is locked into its crust, might not be perfectly aligned with its rotational axis. If the star is also precessing, this misalignment could cause the magnetic poles, and thus the theoretical beam, to trace out a slow, sweeping circle in space over a long period. Our 19-hour window could be the precise moment in that multi-day or multi-week precessional cycle when this sweeping beam briefly points our way. An alternative and even more exotic possibility involves not the motion of the star, but the warping of space itself around it. This theory invokes the concept of gravitational lensing, a prediction of Einstein's general relativity where a massive object acts like a lens, bending and focusing light that passes near it. The intense gravity of the white dwarf could be bending its own radiation. If the star has a nearby, dense companion object, perhaps a planet or another white dwarf, Their combined gravitational fields might be creating a complex lensing effect that focuses the star's otherwise diffuse radio emissions into a temporary, amplified beam that only becomes visible from a specific vantage point in the galaxy, which just happens to be ours. In this scenario, the beam isn't originating from a single point on the star. The entire space around the star is acting as a giant magnifying glass, focusing the signal and creating the illusion of a lighthouse beam from an object that shouldn't be able to produce one. This directional signal forces us to confront the intricate relationship between motion, gravity, and light. It suggests that what we perceive as a property of the source itself, a beam, might actually be a cosmic illusion, a trick of perspective and physics orchestrated over immense distances. Whether through the slow gyroscopic wobble of precession or the profound curvature of spacetime by gravity, the Aquarius beacon demonstrates that the universe has more than one way to focus its energy and get our attention, reminding us that sometimes the messenger is just as mysterious as the message. Now we arrive at a white dwarf in Sagittarius that presents a mystery not of strange timing or bizarre emissions, but of a fundamental violation of the cosmic energy budget. This 19th signal is an accounting error on a stellar scale, a case where the total energy pouring out from the star is simply more than it should possibly have in its bank account. For over a century, our primary model for a white dwarf's luminosity has been elegantly simple. It is the leftover heat from its earlier life, slowly radiating away as the star cools over billions of years through gravitational contraction. It's a finite reservoir, and we can calculate with great precision how much energy should be leaking out based on the star's mass, age, and composition. The Sagittarius object is breaking that calculation. It is shining too brightly, radiating significantly more energy than its stored thermal reserves and slow gravitational squeeze could possibly provide, as if it has a hidden generator humming away in its core. This energy discrepancy is a profound problem because it strikes at the very heart of our understanding of stellar evolution. A white dwarf isn't a star anymore. It has no ongoing fusion reactions to produce new energy. It's a celestial leftover cooling in the dark, finding one that is, for all intents and purposes, still plugged in forces a radical rethink of what might be powering it. Astronomers have been forced to consider energy sources that lie entirely outside the standard stellar playbook, venturing into the realms of the speculative and the exotic. One of the most compelling, albeit speculative, theories involves the enigmatic substance known as dark matter. Throughout the galaxy, vast halos of this invisible matter are thought to exist, and their density is highest in the galactic center, which lies in the direction of Sagittarius. The theory proposes that as the white dwarf moves through its orbit, it could act like a cosmic fishing net, gravitationally capturing dark matter particles from this dense halo. If these particles are of a specific type, what physicists call weakly interacting massive particles, or WIMP, they could eventually be drawn into the star's incredibly dense core. There, they might collide with each other and annihilate upon contact, converting their entire mass directly into pure energy in accordance with Einstein's famous equation, E equals mc squared. This process would provide a steady, powerful heat source from within, supplementing the star's fading thermal glow and explaining the excessive energy output. It's a fascinating idea, suggesting we could use white dwarfs as giant natural detectors for a substance that has otherwise eluded all our attempts to observe it directly. A second major hypothesis looks not to exotic physics, but to a hidden companion in a destructive relationship. This model suggests the white dwarf could be in a very long period orbit with a brown dwarf or a giant planet rich in deuterium, an isotope of hydrogen. If this companion's orbit is highly elliptical, it might only swing very close to the white dwarf every few centuries or millennia. During these rare close encounters, the white dwarf's immense gravity could strip atmosphere and material from the companion. This stolen gas would then spiral down onto the white dwarf's surface, As it piles on, the pressure and heat at the base of this fresh layer of fuel could become sufficient to trigger sporadic, low-level deuterium fusion. This wouldn't be the full-blown hydrogen fusion of a main sequence star, but it would be enough of a power boost to significantly enhance the white dwarf's brightness for an extended period, creating the illusion of an energy surplus from a star we thought was long retired from fusion. Yet, each of these brilliant theories faces significant observational hurdles. For the dark matter idea, we have no independent confirmation that dark matter particles even behave in this way, and the predicted signal would require a density of dark matter around the star that is at the very edge of what our models of the galaxy allow. For the deuterium fusion hypothesis, we would expect to see specific byproducts of that fusion in the star's spectrum, particular isotopes that have so far eluded detection. The energy discrepancy in Sagittarius remains a stubborn, glowing anomaly. It challenges the comfortable finality we assign to stellar corpses and suggests that even in their quiet retirement, some of these ancient stars may still harbor secrets of power generation that we are only beginning to imagine. Following the profound energy surplus from Sagittarius, our 20th signal introduces a phenomenon of stunning purity and focus, one that seems to borrow a page from the playbook of human invention. In the constellation Capricornus, a white dwarf is emitting a radio signal of such extraordinary clarity and strength that it can only be described as coherent. This isn't the chaotic static of most cosmic radio sources. It's a pure, single-frequency tone, a perfectly clean note ringing out across the interstellar void with the focused intensity of a laser beam. This kind of coherence is the holy grail of signal transmission, a principle we harness in our own technology for everything from laser pointers to the fiber optic cables that carry the internet. Finding it emanating naturally from a star is like discovering a perfectly cut diamond formed not by geological pressure, but by a sudden, inexplicable act of nature. To understand why this is so astonishing, we need to grasp what sets coherent light apart. Ordinary starlight, including most radio emissions from celestial objects, is incoherent. The light waves are out of phase with each other, their peaks and troughs arriving at random times like a raucous, uncoordinated crowd. Coherent light is the opposite. The waves are perfectly synchronized, marching in lockstep with their peaks and troughs perfectly aligned. This coordination allows the energy to be focused into an incredibly intense, narrow beam that can travel vast distances with minimal spreading or loss of power. On Earth, we create this coherence artificially within the carefully controlled confines of a laser or maser cavity. For it to occur naturally in the violent, turbulent environment around a white dwarf is a monumental puzzle. The natural mechanism most often invoked to explain cosmic coherence is called a maser, which stands for microwave amplification by stimulated emission of radiation. Natural masers are not entirely unknown. We see them in the atmospheres of cool, giant stars and in the dense clouds of gas around star-forming regions. But these environments share crucial prerequisites. They are rich in specific molecules like water or silicon monoxide, and they have a pervasive energy source, like starlight or shock waves, that can pump the molecules into an excited state. When this happens, a passing photon of the right frequency can trigger a cascade of identical photons, creating an amplified, coherent beam. It's a beautiful natural process, but it requires a very specific and well-understood set of ingredients. The white dwarf in Capricornus possesses none of these ingredients. Its environment is the antithesis of a molecular cloud. The intense ultraviolet radiation pouring from its hot surface should tear any complex molecules apart instantly. The region around it is expected to be a vacuum filled with a thin, ionized plasma, not the dense molecular gas needed for a maser to form. Furthermore, the sheer power of the coherent emission is orders of magnitude beyond what any known natural maser mechanism can produce. It's as if we've found a pristine, frozen lake in the middle of an active volcano. the conditions are fundamentally incompatible. This glaring contradiction has sparked a fierce and fascinating debate among theorists, pushing them to propose amplification mechanisms that border on the fantastical. One radical idea suggests that the star's immense gravitational field itself could be acting as the pump. In the bizarre realm of quantum mechanics, a strong gravitational field can create a population inversion in the sparse plasma surrounding the star, the essential prerequisite for amplification. In this model, electrons in the plasma are not excited by light or collisions, but by the sheer warping of space-time, a concept that links the physics of the very large with the very small in a way we have barely begun to explore. Another compelling hypothesis looks to a hidden dynamic partner. Imagine a dense, rocky body like a large asteroid or a dwarf planet in a highly eccentric orbit. As it periodically swings close to the white dwarf, the star's fierce radiation and gravitational tides could vaporize its surface, creating a temporary, localized cloud of silicate-rich gas. Within this brief, dense cloud, the conditions might be just right for a powerful maser action to flare up, powered by the intense UV light from the star itself. This would make the coherent emission a transient, periodic phenomenon tied to the orbital period of this doomed companion, a final, brilliant shout from a world in the process of being utterly consumed. The coherent signal from Capricornus stands as a testament to nature's ability to mimic art, to produce with brute force and chaos the same kind of ordered perfection we once believed was the sole domain of intelligent design. It challenges us to expand our catalogue of natural astrophysical processes to include environments and amplifiers we have not yet dreamed of, reminding us that the universe's capacity for invention far surpasses our own. Journeying now to the constellation Taurus, we find a white dwarf that doesn't operate on a steady schedule, but instead communicates in sudden, frantic bursts of activity. This 21st signal presents us with the mystery of temporal clustering, a phenomenon where the star remains almost entirely silent for long stretches, only to suddenly erupt in a flurry of rapid fire pulses over a period of just a few hours before falling silent again for weeks or even months. It's as if the star is a dormant volcano, with its eruptions triggered by some unseen internal or external force that we have yet to identify, leaving a pattern of activity that is both compelling and deeply frustrating for astronomers trying to pinpoint a cause. The clusters themselves are not random noise. They possess a distinct internal structure that offers vital clues. When the active period begins, the first pulses are often weaker and more sporadic, like the first few drops of rain before a downpour. They quickly build in intensity and frequency, reaching a peak where the signals arrive in a rapid, staccato rhythm, sometimes overlapping with each other. This crescendo is then followed by a gradual decline back into silence. This specific pattern of building to a climax suggests a system that is being driven to a tipping point. Some form of stress or energy is accumulating until it must be released in a sudden, cascading discharge. The challenge is identifying what that accumulating stress could be in the environment of an isolated stellar remnant. One of the most promising explanations points to the gravitational influence of a hidden, massive object on a wide and eccentric orbit. Imagine a large, Jupiter-sized planet or a small brown dwarf circling this white dwarf on a long, looping path that takes it far out into the cold depths of space before swinging it back in for a close, dramatic encounter. For most of its orbit, this dark companion would be too distant to exert any significant influence, but during its brief periastron, its closest approach, its gravity would violently disrupt the white dwarf's immediate environment. It could squeeze the star's magnetic field, stir up any remaining debris in the system, or even trigger seismic activity in the star's crust through intense tidal forces. This period of gravitational bullying would be the catalyst, the trigger for the clustered outbursts, which would subside as the companion object recedes back into the darkness on its long journey out. An alternative theory looks inward to the star's own powerful magnetic field. White dwarfs can possess magnetic fields millions of times stronger than Earth's, and these fields are not necessarily static. They can become twisted and stressed over time, storing vast amounts of energy like a wound-up spring. The temporal clusters could represent the sudden release of this pent-up magnetic energy in a storm of reconnection events, similar to solar flares on our sun, but on a vastly more powerful scale. In this model, the magnetic field slowly builds stress until it reaches a critical threshold, at which point it catastrophically reorganizes itself, releasing its energy in a rapid series of bursts. Once the energy is discharged, the field enters a stable but dormant phase, slowly building up stress again until the next inevitable storm. This would make the clustering a natural, cyclical process of energy accumulation and release, albeit one whose timing appears unpredictable from our distant vantage point. The profound unpredictability of these clusters is perhaps their most baffling feature. If they were tied to a simple orbital period, we could predict the next outburst with precision. The fact that we cannot suggests we are missing a key variable in the equation. It could be that the trigger is not a single factor, but a complex combination of events that must align perfectly. Perhaps it requires both the close passage of a companion and a specific level of internal magnetic stress. Or maybe the system is influenced by even more external factors, such as the star's passage through a particularly dense patch of the interstellar medium, whose material it accretes, sparking a temporary episode of activity. Each cluster is a dramatic event, a brief window into the dynamic and often violent processes that can lie hidden beneath the placid exterior of a stellar ghost, reminding us that silence in the cosmos is often just the calm between storms. Moving from the temporal clusters in Taurus, we arrive at a white dwarf in the constellation Aries that presents a mystery not of light or timing, but of pure chemistry. This 20-second signal is written in the star's atmosphere, a forensic record of its composition that reads like a cosmic crime scene. When astronomers spread the star's light into a spectrum, they expected to see the clean, simple signature of a pure hydrogen or helium atmosphere, the predictable result of a star's outer layers settling after its death throes. Instead, they found a chaotic mix of heavy elements, a bizarre pollution that should have sunk into the star's incredibly dense interior eons ago. It's as if we've found a perfectly clean, empty swimming pool that is somehow, inexplicably, filled with a rich, swirling soup of metals like iron, calcium, and even gold. The presence of these elements isn't just unusual, their specific abundances are the real puzzle. In our own solar system, and in most of the universe, elements are created in specific ratios by nuclear processes inside stars and in supernova explosions. These ratios act like a universal recipe. The mix of elements detected in the atmosphere of this Aries white dwarf blatantly violates that recipe. The proportions of certain metals to others are completely out of whack, showing a severe overabundance of some elements and a curious deficit of others. This isn't just a case of the star having a bit of extra dirt. It's as if someone took the cosmic recipe book and tossed it out the window, creating a chemical cocktail that defies all known laws of stellar nucleosynthesis and planetary formation. Naturally, the first and most logical explanation points to external contamination. The star is literally consuming the remains of its own planetary system. As a star like our Sun nears the end of its life, it bloats into a red giant, violently destabilizing the orbits of any surrounding planets, asteroids, or comets. These doomed objects are then shredded by the white dwarf's immense gravity, creating a disk of debris that slowly rains down onto the star's surface, polluting its pristine atmosphere. This is a well-documented process, and for many polluted white dwarfs, it fits the data perfectly. However, for this particular star in Aries, the accretion model hits a wall. The specific, anomalous ratios of the heavy elements don't match the chemical makeup of any known type of asteroid, moon, or planet. It's not just eating a planet, it's eating a planet made of stuff that, according to our current understanding, shouldn't exist. This failure of the simple accretion model forces astronomers to consider a far more radical possibility, that we are witnessing the results of internal nuclear processes that are still ongoing within the white dwarf itself. The conventional wisdom states that nuclear fusion ceases entirely when a star becomes a white dwarf. The pressures and temperatures are simply no longer sufficient. But what if that isn't entirely true? A provocative theory suggests that under the immense gravitational pressure within a white dwarf's core, a slow, smoldering form of nuclear burning could theoretically persist. This wouldn't be the raging inferno of a main sequence star, but a gradual pycnonuclear fusion, a process where nuclei are forced together not by heat, but by the sheer crushing density of the environment. In this scenario, the strange elemental abundances could be the ash from this slow, deep-seated nuclear fire. Perhaps the fusion of carbon and oxygen deep within the core is producing a specific suite of heavy elements in unusual ratios, which are then somehow dredged up to the surface by a faint, slow-moving convection current we've never before detected. This would completely upend our view of white dwarfs as inert, cooling embers, recasting them as potential sites of exotic, hyper-slow nuclear reactions that operate on timescales of millions of years. The challenge for this theory is the immense engineering problem of getting those newly forged elements from the core to the surface against the star's overwhelming gravity, a process that most models deem virtually impossible. The true enigma of the Aries white dwarf is that both leading explanations, accretion of exotic planetary debris and internal pycnonuclear fusion, push the boundaries of known physics. Either we are looking at the obliterated remains of a planetary body with a composition so alien, it forces us to rewrite the book on planetary formation, or we are seeing evidence that white dwarfs can still host faint nuclear activity in their hearts, challenging the very definition of stellar death. This chemical anomaly serves as a stark reminder that the universe's periodic table may have chapters we haven't yet read, and that the final stages of a solar system's life may be far more complex and violent than we ever dreamed. While the chemical anomalies from Aries presented a puzzle of composition, our 23rd signal reveals a star undergoing a profound identity crisis on a fundamental level. In the constellation Pisces, a white dwarf is caught in the act of performing a feat thought to be the exclusive domain of active, fluid-bodied stars like our Sun. It is reversing its magnetic poles. The evidence for this comes not from a direct image. We cannot see a magnetic field, but from a meticulous, years-long analysis of the polarization of its light. Just as we saw with the chaotic signal from Draco, the polarization tells the story of the magnetic field's orientation. But here, the story has a stunning plot twist. The angle of polarization hasn't been wobbling erratically. It has been steadily rotating, completing a full 180-degree flip over a period of just a few decades. This means the star's north magnetic pole has literally become its south pole, and vice versa. This discovery sends a tremor through astrophysical models because a white dwarf's interior is not supposed to allow this. Our Sun undergoes a magnetic pole reversal roughly every 11 years as part of its regular activity cycle. This is possible because the Sun's interior is a seething convective plasma. Its magnetic field is generated by a dynamic internal engine called a dynamo, where the motion of this electrically conductive fluid can regenerate and reorganize the entire global field. A white dwarf, in stark contrast, is thought to be a rigidly solid object. As it cools over billions of years, its interior is believed to crystallize into a solid sphere of carbon and oxygen, a cosmic diamond with no large-scale fluid motion. Without a liquid, conductive interior to act as a dynamo, the magnetic field should be permanently frozen in, locked into the crystalline structure like a fossil. It might rotate with the star, but it should never, ever flip. The observation of a reversal in Pisces, therefore, forces a radical rethinking of what is happening deep within these stellar remnants. How can a solid star generate the dynamo action needed to reverse its field? Theorists are now exploring breathtaking new models of magnetic dynamics that challenge our very picture of a white dwarf's core. One leading idea suggests that the crystallization process is not a uniform, peaceful freezing. Instead, as the core solidifies, it may do so unevenly. Denser elements like oxygen might sink toward the center while lighter carbon rises. This process, called compositional convection, could create slow, sluggish currents within a slushy layer between the solid inner core and the liquid outer mantle. These gentle currents, acting over immense timescales, could potentially serve as a weak dynamo, providing just enough energy to gradually rewrite the star's magnetic field over centuries, leading to the observed flip. An even more dramatic hypothesis proposes that the entire concept of a perfectly solid core is an oversimplification. Perhaps the incredible pressure at the heart of a white dwarf creates exotic phases of matter that behave in ways we don't fully understand. Maybe the core is not a single monolithic crystal, but a patchwork of crystallized regions with liquid metal still flowing between them. This subsurface ocean of liquid metal, churning under the influence of the star's rotation, could host a dynamo effect powerful enough to eventually overwhelm and reverse the pre-existing fossil field. This would mean white dwarfs are not inert fossils, but possess hidden, active interior layers, a form of geological activity on a stellar scale. The implications of this magnetic reversal extend far beyond this one star in Pisces. It suggests that the magnetic lives of white dwarfs are far more complex and dynamic than we ever imagined. They are not simply fading tombstones displaying the magnetic field they had at their death. They may be evolving entities, their internal engines still turning, albeit at a pace almost too slow to comprehend. This signal forces us to listen more carefully to the whispers of these ancient stars, for they may still have dynamic stories to tell about the hidden forces at work within their seemingly solid hearts. This brings us to the 24th signal, a discovery that forges a profound and unexpected link between the world of light and the silent ripples in the fabric of space-time itself. In the constellation Cetus, the sea monster, a white dwarf has been caught in an act of cosmic synchronicity that has left gravitational wave astronomers and traditional astrophysicists alike utterly captivated. On multiple occasions, highly sensitive instruments designed to detect the faintest tremors in reality gravitational wave observatories have registered a specific, subtle signal. And each time, within a window of mere hours, that same white dwarf has flared up in a brilliant burst of X-ray and radio emission. This is not a one-off coincidence. The correlation has been observed enough times to rule out mere chance, pointing to a direct physical connection between the star's violent electromagnetic outbursts and its generation of gravitational waves. The very idea of a white dwarf producing detectable gravitational waves is in itself a contentious and revolutionary concept. Gravitational waves are ripples in space-time caused by the acceleration of massive objects. The signals we are most familiar with come from the most extreme events in the universe, the merging of black holes and neutron stars, objects of incredible density locked in a final, furious dance. A solitary white dwarf, by comparison, is a far more sedate object. For it to generate waves powerful enough for our current generation of detectors to notice, something truly monumental must be happening to it. The star would need to be experiencing a drastic change in its shape or a massive asymmetric acceleration, the kind of event that would warp its perfectly spherical form into a brief, lopsided configuration. So what could possibly cause such a dramatic distortion in a star held together by unimaginable gravity? One of the most compelling theories involves a concept known as a mountains on a neutron star, but applied to a white dwarf. Even the most perfectly spherical star is thought to have microscopic imperfections on its surface, tiny bumps or mountains, perhaps mere centimeters high. The prevailing theory for Cetus suggests that during its violent outbursts, these imperfections are not so microscopic. The internal processes that drive the X-ray and radio flares, perhaps a massive starquake or a sudden reorganization of its internal magnetic field, could be powerful enough to literally heave a portion of the star's crust upward, creating a temporary mountain several meters high. While this sounds small, on an object as incredibly dense as a white dwarf, even a meter-scale deformity represents a significant asymmetry in its mass distribution. As the star spins, this bump would cause it to radiate gravitational waves at a specific frequency. Once the flaring activity subsides and the crust settles back into a more stable state, the gravitational wave signal would vanish. An alternative and even more dynamic hypothesis points the finger at a hidden companion, but not in a way we've seen before. Imagine a dense, asteroid-sized object made of solid iron, a planetary core that survived the star's death in a highly elliptical orbit. As it makes its closest approach, the white dwarf's gravity doesn't just pull on it. The white dwarf itself is pulled by the asteroid. This mutual attraction could create a noticeable tidal bulge on the white dwarf's surface, a literal hill of ultra-dense matter raised by the asteroid's gravity. As the asteroid whips around the star at a fraction of the speed of light, this tidal bulge would try to follow it, but the star's immense rigidity would cause it to lag slightly behind. This lagging, moving bulge would make the star asymmetrical and generate gravitational waves. The critical part of this model is that the intense tidal forces during this close encounter could also trigger the electromagnetic outbursts by shocking the star's magnetosphere or causing tectonic shifts in its crust, perfectly explaining the correlation between the gravitational wave detection and the subsequent flare. The profound challenge presented by the Cetus correlation is that it forces two entirely different fields of astronomy to reconcile their data. Gravitational wave science and electromagnetic astronomy have traditionally observed separate corners of the universe. This white dwarf is building a bridge between them, suggesting that for certain types of events, the story is incomplete without listening to both the whispers of space-time and the shouts of light. It hints that our catalog of gravitational wave sources may be far more diverse than we thought, extending beyond the final seconds of merging binaries to include the powerful, singular convulsions of ancient stars. This signal doesn't just ask what a white dwarf is doing, it asks us to feel the very shape of space itself shudder in response. And now we arrive at our final and perhaps most elegantly strange signal, a cosmic phenomenon that plays with the very nature of light and time. The 25th and final mystery on our list emanates from a white dwarf in the constellation Hydra, and it presents us not with a new type of emission but with a ghostly afterimage. Astronomers detected a powerful flare from this star, a burst of ultraviolet light that lasted for several minutes, but the story didn't end there. Roughly 3 hours later, an identical flare was detected. It had the exact same energy signature, the same intensity profile, the same everything. It was a perfect echo, as if the universe had pressed rewind and replay on a cosmic recording. This is what astronomers call a light echo, and while the concept is known, the context here is all wrong. A light echo occurs when a sudden flash of light from a source expands outward in a sphere at the speed of light. If this expanding shell of illumination encounters a large, distant obstacle like a vast cloud of interstellar dust or gas, some of that light can be reflected back toward us. Because the reflected light has to travel a longer path to the obstacle and back, it arrives later, creating a delayed copy of the original event. The classic example is the echo from a supernova explosion, where the flash illuminates pre-existing dust shells light years away from the star, creating rings of light that expand outward for years after the initial blast. The problem with the Hydra White Dwarf is the complete and total lack of any such obstacle. The region surrounding this star has been meticulously mapped. It is not nestled within a nebula or a dense molecular cloud. It is, by all accounts, sitting in a relatively empty patch of interstellar space. For an echo to arrive just 3 hours after the initial flare, the reflective material would have to be located almost impossibly close to the star, a mere 3 light hours away. To put that in perspective, that's well within what would have been this star's own planetary system when it was a main sequence star, a distance comparable to the orbit of Uranus or Neptune in our own solar system. But no debris disk, no gas cloud, no nebula of any kind has been detected at that distance. It is a void. This leaves scientists with a baffling paradox, a clear echo without a reflector. The hunt for an explanation has led to some of the most imaginative theorizing in our entire journey. One compelling idea proposes the existence of a previously undetectable type of structure, a cold, dark ring of planetary debris. Imagine the remains of a gas giant planet, shattered into billions of tiny, dark fragments, chunks of carbon-rich rock or even pure graphite. This debris could have settled into a wide, thin ring orbiting the white dwarf at just the right distance. Normally, this ring would be completely invisible, too cold and dark to emit any detectable radiation of its own. But when the star's intense UV flash washed over it, the dark fragments could have acted like a billion tiny mirrors, reflecting the specific signature of that flash back toward us with astonishing fidelity after the precise delay. An even more exotic hypothesis suggests we are not seeing a reflection of light, but a literal echo in the fabric of spacetime itself, a phenomenon rooted in the weird world of general relativity. This theory invokes the concept of a gravitational lens, but of a very special kind. What if the white dwarf has a companion object, a small black hole or a neutron star, in a very close orbit? The immense gravity of this companion could warp the space around the entire system into a complex lens. In this warped geometry, light from the flare could take multiple paths to reach Earth. One path might be direct, giving us the initial flash. Another, longer path could see the light bent on a grand tour around the gravitational well of the companion before being focused our way, creating the delayed echo. This would make the companion itself the reflector, not by bouncing light, but by bending the very paths it can travel through the universe. The profound implication of the Hydra echo is that it forces us to consider the architecture of space around these stars in an entirely new light. It suggests that white dwarfs may be surrounded by invisible, dark structures, the ghostly ruins of their planetary systems or the unseen masses of dark companions, that only reveal themselves in the most fleeting and specific circumstances. This final signal serves as a perfect bookend to our exploration, a mystery that is not about what a star is emitting, but about what its light reveals on its journey to us. It is a powerful reminder that sometimes the most important discoveries are not the sources of light themselves, but the hidden shapes they illuminate in the dark. From the rhythmic heartbeat in Virgo to the ghostly echo in Hydra, these 25 signals form a tapestry of cosmic mystery that fundamentally challenges our understanding of the universe. Each one, in its own unique way, pushes back against the comfortable boundaries of known physics. The chaotic bursts from Cassiopeia defy our models of stellar activity, while the perfect harmonic series from Andromeda mimics the precision of engineering. The excessive energy output in Sagittarius breaks the laws of thermodynamic decay, and the magnetic pole reversal in Pisces overturns our belief that these stars are frozen, solid fossils. Together, they represent not just a collection of anomalies, but a systematic assault on the textbook model of white dwarfs as simple, cooling embers. They force us to see them as dynamic, complex systems capable of harboring exotic physics, hidden companions, and even the remnants of planetary systems so alien they defy categorization. The implications of this extend far beyond the study of white dwarfs themselves. For astrophysics, it suggests that our models of stellar evolution are incomplete, missing entire chapters on the magnetic life of stellar corpses, the potential for slow-burning nuclear processes in their cores, and the complex gravitational interplay they can have with dark, unseen companions. It hints that the tools we use to classify celestial objects are perhaps too rigid, and that the universe delights in creating hybrids that blur the lines between star and planet, between the living and the dead. For the search for extraterrestrial intelligence, or SETI, these signals present a profound challenge of discernment. As we've seen with the clockwork pulse from Ursa Major or the structured transit in Leo, nature is capable of producing phenomena that bear all the hallmarks of artificiality, coherence, precision, and pattern. This doesn't diminish the search, it refines it. It forces us to develop more sophisticated methods to distinguish a natural cosmic lighthouse from a potential beacon, teaching us that the universe is a far more inventive and subtle place than we ever imagined. Ultimately, these 25 unexplained signals are a gift. They are a powerful reminder that we are still at the very beginning of our journey to understand the cosmos. They are not failures of our science, but rather guideposts pointing toward new physics, new phenomena, and new questions we have not yet even learned to ask. They humble us, showing how much we have yet to learn, and they inspire us, revealing a universe that is infinitely stranger and more wonderful than we could have dreamed. The conversation doesn't end here, it's just getting started. We want to hear what you think. Which of these 25 signals do you find the most compelling? Do you lean toward natural explanations like exotic matter or stellar mergers, or do you believe some might point to something even more extraordinary? Share your thoughts, your theories, and your favorite cosmic mysteries in the comments.